and welcome to another episode of Lexx Education, the comedy science podcast where comedian me, Laura Lexx, tries to learn science from her normal brother Ron.
Hello, I'm Ron.
Hi Ron, you're so normal.
I'm very normal.
Same room episode.
Same room episode, attic record.
Sat so close to each other.
So warm in here.
It is. Do you want to open a window?
Yes.
Yeah, okay. We're sharing headphones because it's a special episode today. It's our first ever guest episode. We've never had a guest before.
We're not going to top this, so we'll probably not have another one.
I imagine he's excited to be here too. This will probably be the most exciting science project he's ever been involved in. We would love to introduce you to your ears, our substitute teacher for the day. It's none other, I don't know how he's here, it's Dara O'Briain.
Hello everybody, how are you? Am I really the first guest?
Yeah.
Oh man, do you want me to get you some guests? I'll put a call around and you'll be like David Attenborough tapping on the glass going, oh, hello, what is this? The kind of a thing. Yeah, absolutely. I was once threatened by David Attenborough. This is my favourite nerdy story of all time. I was once threatened by David Attenborough.
What?
It was
with what? Like a wildebeest?
I've written a kid's book about science and it mentioned animals in passing. I'm standing waiting to do an interview about it, like pre-Christmas, in that there's a part of Radio 2 where you wait before you do all the shows. And David Attenborough came in. He was obviously on after me or on a different show or whatever. And I sat down. I've met him a couple of times. And I said, David, how are you? Chat. And then I said, David, I should tell you this. I've written a book and I do mention animals in the book. And David Attenborough leaned in and went, you get space. I get And I've taken to be totally that he meant it totally like as hey, back off. This is my world, son. You don't step in on animals without really putting the time in. So so that was.
Do you stand a bit taller that day? Like David Attenborough was a little bit threatened by me. Like I could...
it was just I did bants with Attenborough. You know what I mean? Like So it was lovely. So look, I'm deeply flattered to have been invited.
You shouldn't be. You shouldn't be at all. You should be so depressed that you're here. You should be...
Honestly, it's lovely to, I did nothing I like more of an evening than talking about science. But I'm also aware of your general antipathy towards the beautiful science that is physics, that you're not going for it. You're not going for it at all, are you?
I think it's stupid. I think it's very much giving maths sums to things that were happening anyway. That we've just been covering scalars and vectors.
Okay,
and
cool. Yep.
Ron assures me it's the basis of how everything works.
A friend of mine actually texted me a quote from this week's episode. It's just useless. It's intellectualism for the sake of it, is your description of physics.
Because we had to work out how long it took me to do a journey I didn't do.
Yeah. Have you never had a hypothetical comedy routine? Have you ever spoken about...
Yeah, but that's got a purpose. That makes people laugh. This was just sad.
All it is a lot of it's training. A lot of it's training for a thing you will never do. Look, I get it. A lot of maths, for people who don't go on to use it, is like doing star jumps and then wondering where are all the star jumps in adult life. I did so many star jumps in school. It's amazing. Adult life didn't seem to involve running around a field, but people don't credit because people get the point of doing star jumps just as a kind of as a general health thing. So I'm afraid scalars and vectors are just a general health thing. Your brain, despite you, has become slightly more ripped because you now know there's scalars and vectors.
I think it's curdled. it's not
you
even...
do know there's scalars and vectors. You do know the difference that one is just a number.
They're both just numbers, Dara.
No,
they're both just numbers.
They're really both
hours on
numbers.
this.
They're really not both just numbers, right? The one is a number and an extra bit. It's like a two-dimensional number. Because it has another piece of information contained within it. One is just a number. One is just a thing, like whatever. How tall are you? But the other one is...
The other one is how tall would you be if you'd bent over and wandered away?
How long are you and in what direction? The other has a second thing added to it as well. So it's
I just feel like only the one that is where you actually got to, that's the only one that matters.
As in, like, are you still on the train journey that you never made, that we worked out how long it took you to? Is that sorry?
Well, like, you know, if I'm 200 miles away, that matters. It doesn't matter whether the M40 was a longer journey than the M1.
Yeah, but hang on. It doesn't. Surely it matters which direction you're 200 away in.
Oh, that depends.
Well, like, if the gig was... If you were leaving London and the gig was in Woking and you end up in Sevenoaks, then the second part of the vector, the direction part of it, is really, really important as well.
But then what was the other bit that was like, that was the journey, even though you went to Woking, sometimes you were, listen.
But one was the distance you travelled and one was your displacement from where you started. And I tried to turn it into a fun little story where we got paella on the way, but...
I can kind of see where that was difficult. Here, for example, at some point you're going to talk about orbits, presumably, because this is space, right? You're going to talk about orbits, right? And, you know, do you understand what an orbit is?
The chewing gum?
No, not the chewing gum. The thing from which the chewing gum took its name. That's very important to get the order of these correct, right? However, like, this is often tricky. Pluto isn't named after the cartoon dog. The Pluto is named first. Pluto is actually a Greek thing, and it was a 10-year-old girl who won, and she won a £5 note for coming up with the name of Pluto. They had a public competition. Yeah, and so she came up with the name for Pluto because they discovered Pluto. They saw it doing its thing, or they saw reverbing things around it, and found and thought would look and saw Pluto for the first time. Huge thing, 1930s. So people hadn't discovered anything in about 100 years, another planet in about 100 years, and so they had an international competition, and some girl came up with the name Pluto.
But then it isn't a planet now.
It's not a because it turns out it doesn't do enough. It's kind of
right. This is one of my questions, and I checked with Ron whether this was a stupid question beforehand. What is a planet, and why isn't the moon a planet?
Because we just keep the word planet. Obviously, look, they're all big round lumps in space, right? So in that regard, you can stick them together, right? What matters is how kind of strong and independent it is really what we're talking about here. And we keep planets for things that, because if you imagine, it all started with a big cloud of dust, right? All the things are made by clouds of dust, and what happens is gravity kind of begins to swirl them and swirl them, and these things begin to stick together, and they clump. Clumping is the most important word in astronomy. Clumping, bits of it just kind of bump together.
Do you see what I mean now about them just making stuff up? You can't just be like clumping. You get clumping. Yes.
You know, the single most. If you want to understand astronomy, do you remember when you took a poster off a wall and there's bits of blue tack, and you used a big bit of blue tack to pick up the smaller bits of blue tack, right? That's space. Everything in space is that crap. So bits of things clump other bits of them together, right? Usually in the middle of it there'll be a huge one, which will be a star. Because a star is basically loads of dust and gases basically pulled together, and then they squish, and it gets so big it squishes stuff in the middle, and it forces them together, and that explodes, and it creates all these, and it's a series of explosions of things being squished by how big the star is. Okay, we may come back to this. Okay, point is, outside the star there's still a big disk of dust. Okay. Big disk of dust, right? And some of that clumps together, and it sort of spins because gravity makes it spin, and the bits of it clump together into little regions, little lumps, basically. And they clump together into these little lumps, and those become planets. Okay, because they are, if you think, the king of it all is a star in the middle. The lumps that go around that star, they're the planets.
But we're all just dust balls.
No, look, we're sitting on one at the moment.
Yeah.
If you pull enough dust together hard enough, it turns into...
You know, like sometimes when you look under the bed and there's like little dust balls, that's the start of a planet.
Yeah, dust. Well, look, dust is a very strange thing. Dust is a lot of definitions. Dust is a weird thing. Dust covers a lot. Both at home and in space. Dust is a really nicely vague term for just bits of matter, essentially, but they're all lying out in the big, and they kind of accrete, they clump together, and the ones that go around the sun.
Hang on, where did the dust come from?
The dust came from, firstly, from the creation of the universe, Big Bang, threw out loads of stuff, and then stars clump together and they create other elements. They all start with hydrogen. The stars make other elements. This is Yes, that's the face. Stars make all the elements. They bar hydrogen
With the covalent bonding.
No. With the
No.
squishing together.
Squishing.
Fusion.
They squish
Fusion.
them into other. They fuse them by just squishing them together. So hydrogen gets squished until it becomes helium. All right. So
I
basically,
didn't know you could squish me.
Hang on. See, hydrogen,
Yeah?
1 proton in the middle, helium 2. So they get
Squishes.
Yeah.
That's
It
another
builds up
way.
like that.
This is my periodic table.
Yeah, exactly. So helium is
The
slightly bigger.
sandcastle of stuff. That's what I call it.
Yeah, so helium is slightly bigger than hydrogen. It's slightly heavier than hydrogen. It's actually two things squished together. But the process of squishing the hydrogen together, there's a little bit extra stuff left over. And it's a kind of complicated process, obviously, but there's a little bit extra stuff left over, including lots of energy comes out, and that causes all the heat that's happening. But in the centre of the sun, even this week now, it's a big furnace that basically is squishing hydrogen to make helium. And then it starts squishing the helium to make other things, carbon and things like that, and then squishes those. If it can keep going, if it's big enough to keep going and going and going, it'll squish those to make heavier things. It'll squish those, and eventually a supernova will cause a massive squishiness, loads of things, big things to squish together and create all the really heavy things, bigger than iron things. So everything is made in stars.
I really hope that there are some science books out there called like Squishing and Clumping.
Squishing and clumping.
Secrets to it all.
It's all squishing and clumping. Yeah, it's grand. It's good. Squishing won't be one because it's not like you're making them smaller. You're just pushing them together. You're basically pushing them together. What would be an excellent example of this? 2 Rolos. If you wanted to make a super Rolo, so you just better yet, 2 not Maltesers. Let's go for minstrels. They have a hard shell. So let's presume that there are lots of complex forces that don't want things to be squished together, but you can overcome them you can overcome the hard shell of a Malteser by just pressing hard against another Malteser until you push it together. It cracks that hard shell, and you create super minstrel. Sorry, not a Malteser. Super minstrel. A Malteser would complicate things because of its honeycomb shell. Let's not do that. But you create a super minstrel, which is basically so hydrogen is just a minstrel, and you get another hydrogen, you push them together, you squeeze them really hard until you crack that, you get past the bit where it has to crack, and then you squish them together into being super minstrel, and that's helium. And then you've got a load of super minstrels, and what you do is you push them together as well, and the force is sufficient to crack them together to make other things, and then the other things get squished together, and so on. So the process basically builds up more and more of the elements. All the elements basically have to be built like that by taking minstrels.
Flapping about the sun.
Sorry?
They're just all flapping about in the sun.
Well, the sun is basically a big ball of.
So
of
could you
hydrogen.
just suddenly boop, a bit of lead appears?
Let it down there, because basically you need to have a shell, you need to have a supernova, I think, to create lead. As far as I'm going now, into the point where you need a massive amount of force.
Heaviest you can get in the first instance.
And that force takes big, heavy elements and smashes them together. So getting all the way up to the top of the chain is quite difficult to do.
Right.
So we live in a universe which is a lot of hydrogen and a lot of helium and a lot of carbon, and a lot of the simpler ones, and then the really, really big ones, gold, whatever. That's why they're in such rare supply, because not that many stars have gone through the different generations or have been big enough to get to the point where we make lots of gold. So that's the thing. The universe is full of diamonds, but it's not full of lots of gold. That's one way to look at it. So you basically squish them all together to make it. And the act of squishing, the bit where the shell of the minstrel cracks, right? That bit where you go, great, I've got them together, right? That bit in the actual physics is a massive release of energy, and so that's why it's so hot. And then it releases all these photons of light, and they bang, 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 bang around the middle of the sun for literally 1 million years until they reach the outside of the sun, and then they come out as sun rays. So it's got that action of cracking the 2 minstrels together, of squishing them together to make a big minstrel, like a bigger element, releases a load of light, basically. So if you imagine, 2 minstrels, you push them together, and you push them, and then eventually you went over some boundary, basically, you went click, and it squished them together, loads of light appears when you do that.
Okay.
So we saw the heat of the sun. So, and also within the sun, then the sun is a big ball of light just bouncing off all the bits of ping, 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 and slowly, on average, it takes 1 million years to get from the middle of the sun to the edge of the sun, where it just goes and shoots off into space. takes 8 minutes to get to us and 1,000,000 years to get from the middle of the sun to the edge of the sun. Yeah. But anyway, so that's always happening in the middle. It's just...
That's like that feeling, when you're on a train and they're like, this train will divide, and then it takes like 40 minutes to divide, but you're getting off at the next stop anyway. So you're like, my God.
Yeah, just build a longer platform. That's always the situation. Or why can't people just climb down onto the ground and walk along and then climb back up onto the platform again?
Yeah.
I don't know why.
It's only an 8-minute journey. Why is it taking me 1,000,000 years to get to the edge of it? Livid, like being at Euston when it's busy.
They don't say, oh, by the way, this house you're looking at, this house, they'll say, look, it's wonderfully located. It's a 23-minute journey to Waterloo. They won't go, but you have to be in the first 4 carriages or you're going somewhere else. That warning is never applied. Anyway, so that's what's happening in the middle, right? In the middle of all of our solar systems. And on every bright dot you see in the sky, bar a few, most of the bright dots in the sky you see, that's it.
Do you listen to this sciencey stuff here? Because this is science now, where you say a rule and then you sort of mumble.
Oh, no, I only say...
except for everything else.
Some of the bright stuff you see in the sky are planets. If you look up in the sky,
dust balls,
you'll see, and we'll get to why
cold dust balls. We've got cold dust balls and hot dust balls.
They're not cold. Venus is really hot. But you'll also see them. So from Earth, you'll see the other planets, and they'll also be dots in the sky. And people sometimes mistake them for stars.
Idiots. Yeah. Is Venus actually green?
It's no, it's not necessarily.
This is the other problem with science. Is the more you learn about it, the more all the cool stuff isn't real.
Venus is incredibly cool.
You just said it was hot.
Hey, boom! Venus has clouds of sulfuric acid raining constantly all the time.
That sounds brilliant.
We when the Russians failed in getting to the moon, they shifted their focus to getting to Venus instead, and they landed a series of probes on Venus, and the longest any of them lasted was 90 minutes. They kept getting through the atmosphere, and then be hit by sulfuric acid rainstorms and just dying, and they'd send another one up, and then I think the most they ever got out of it was like an hour or 90 minutes before the thing just went, no.
Send it out with one of those golf umbrellas, the real thick ones.
Honestly, there's no point. Then you're just holding, like that cartoon, so I'm just holding an umbrella with just the metal bits. So it instantly does that, like whatever. So it's really, really, Venus is awful. Venus is a terrible place, the worst place in the solar system.
It is just, so if it's like... But there is actually a ball in the middle of it, is there? There is
there is for those. There is a debate about the further ones out. Basically, if you imagine, we had a star, and then there was a disk of stuff, basically. Dust. Let's go back to dust.
More dust.
Dust and gas.
But this is a disk of dust. A disk of dust. Ooh,
dust and gas. Right. Heavier stuff was contained in near the middle, and the lighter stuff, where the star got formed, pushed out the lighter stuff, so it was on the outside. So in other words, when you look at our solar system, it's rock, and then it's gas.
Scissors, paper.
Gas. No, there's no scissors or paper.
Scissors, paper.
No scissors, dust. Paper. Nothing beats rock. Gas beats rock in many ways, and that's not helping in any way. But anyway, heavy stuff is in the middle. So Mercury, Venus, Earth, and Mars are all rock planets. And then there's a band of asteroids, basically. And then you get out to...
Are they small planets, kind of?
They're some of them are regarded as dwarf planets, yeah. Because that's the distinction we have, yeah. Planets are the things that are like, they're big and independent. They do their own thing. They go in a big circle. They clear that circle. That's really important. They're big enough so they end up being regular shaped. As you can see, all the ones that I've listed there are all regular shaped. They're big. They're ellipsoids, the circles, basically. And so they're all doing that. They're all planets, and then moons are stuff that's stuck to the planet, and they just go around the planet, and that's the distinction. They're also sometimes there's sometimes like our moon is a sphere, but sometimes there are really uneven things like the ones that outside Mars, Phoebus and Deimos are weird shaped ones.
Is stuff still getting stuck to the moon then?
Oh well, we have cleared most of the dust out. Occasionally stuff gets bombarded and rocks come in from outside comets on long arcs, and they just bump into them as well. So
the moon's not like working on gearing up to being a full planet. It's not going to get promoted.
It will never be. What will happen is slowly the moon, and it's maybe confused. The moon is slowly moving further out from us.
Oh no!
Yeah, I know.
I love the moon.
And the moon is cool. The moon's great. I mean, watch my Channel 5 documentary about the moon. The is coming out in a few weeks' time. But the moon is cool. Because of the moon, we have a 24-hour day. We used to have a 4-hour day when the planet was formed. Then the planet was formed about 4.5 billion years ago, right? About 200 million years after that, this is the current theory, something smashed into Earth, right? A big rock smashed into Earth, dislodged a load of stuff, and over time clumped together to become the moon.
Oh no, so the moon used to be part of us, and it's just so, it must be so lonely now, just hanging around on the edge like, hey guys, do you miss me?
It's really dead because it was volcanic for a while, but it's not volcanic anymore.
I was probably actually looking at the Earth and like, thank God I got away. Look what the humans are doing to it.
I don't know. The moon's kind of an abused partner though, because it kind of just sits out there taking a lot of flack for us.
Oh, does it?
Hit. Yeah, it's riddled with craters.
It shielded us from a lot of it wasn't a great bombardment. It took the hit of a load of stuff.
I love him even more now.
Also, you've got to if we're anthropomorphizing moon, you've got to decide which side is it the side facing us that is the anthropomorphic side, or is it looking out, because we never see the other side of it, because the moon is damped and it would spin like everything else spins.
It's damp.
It's damped. What it means is basically the moon shifts the water around, pulls the water around the planet.
Yeah,
okay?
I think that's not true, but
it's very, very, very much true. Yeah, it's very.
I cannot understand how that could.
Just gravity.
Yeah, but
okay. Imagine it's static. Imagine it's still. Imagine a still thing. You've got a planet, right? Us. Okay. You've got a moon, and our moon is relatively the biggest moon in the solar system.
Yeah, it is.
But relative to us, there are bigger moons on other planets, but they're bigger planets. But so in terms of the effect that the moon has on us is bigger from our moon than any other moon in the solar system. So yeah, our moon punches above its weight. Well done, our moon. Buddha boss. Well done. Congratulations, right?
It's Moon Monthly.
Yeah. We're very pro moon. But if you imagine the moon is sitting here, right? Pulling, because there's gravity, pulling on Earth, right?
But why isn't our gravity pulling it harder?
It is equally pulling. That's why it's not flown away. So we're kind of pulling on each other. Imagine there's elastic cord.
You know?
What?
I'm so stupid sometimes. Yeah, because the water's staying on the planet. You're right. I agree, actually.
But the water does get drawn to the moon on one side, right? And on the other side, really weirdly, because it's the farthest part away, it moves away from the moon. So it's sort of like our planet in an extreme form. If you imagine our planet is a circle and the water is like a rugby ball on top of that. It's obviously not that much. It's not that pronounced.
This is where you got the idea that the moon was squeezing the Earth, which was a theory Laura had for some time.
It was this, but Dara's explaining it better, that's all. Yeah.
So basically, and as it moves around, it sloshes the water around. And so
the stuff at the back is like, oh, you're too far away, I'm going to go away too, I don't even need you.
I'm going to fall back because you're pulling me less than you're pulling the rest of stuff. Like, so you end up with two peaks. You end up with a peak on either side of the planet.
God, I think it must be awful being the sea. You just
I'm not sure if
always all over the place.
Everything is helping your physics here.
I can't help it. I
get it as a defense mechanism that you have to personalize thing, but the sea is too huge to anthropomorphize. It's too big and amorphous, and it covers. It's like 71% of the surface. You know.
Yeah.
I mean, are you saying the Atlantic and the Pacific are they all one character, or are they a series of interconnected?
Well, I'm worried about them now because they're just spending their whole life trailing about after this rock in the sky.
The sea has bigger problems than the moon.
I know, the orcas. They're up to stuff at the moment, aren't they?
Imploding billionaires everywhere.
Yeah.
I would say it isn't trailing. It's more reaching for the moon than it is trailing around. And actually, weirdly, because the moon is moving independently, it's kind of dragging behind it. Or no, is it, dragging it, or is it pulling it along, I think? Anyway, one of the two.
Oh, so the sea is like the moon's comfort blanket.
Maybe, yeah. Maybe that's a way to put it. But anyway, it's
just the sea.
It's like constantly yearning, and because of that, it's slowing the moon down, which ironically makes the moon move further away. Because if the moon,
you would. You
Yeah, you
can't
would.
be in a constant relationship with someone that's dragging you down. You have to break away.
You can't. You've got to just. You need your own. You need your own. And yeah, I just don't want to say space at this point. You need your own. Arena. You need your own area just to yourself. So our moon is slowly moving away from us. It's slowing our day down. As I said, we had a 4-hour day before the moon came along, and now we've got a 24-hour day. So that's taken us,
Wow.
whatever, 4.3 billion
I bet the
years to
Daily
do that.
Mail had a lot to say about that when there was only a 4-hour day. These
Oh, you
work
think
shy layabouts copying the Scandi work week with their 4-hour days.
So that's what satellites, moons just kind of hover around something. I mean,
Okay.
it is. I get why it would be confusing, because we just hover around the sun, right?
Yeah.
We're just hovering around the sun, and the sun is part of like a galaxy that just spins around a big black hole in the middle of the Milky Way, so we're all spinning around stuff, and then that whole stuff is kind of moving. So there's a lot of movement.
So we could be a moon of the sun if we decided to term it that way.
You could absolutely name it that way, and then we have moons of us. Yeah, you could entirely say that, and also you can then send a satellite up to be a moon of the moon. There is you could have a moon of the moon, which is a moon of us, and we are a moon of the sun. They're just names for what's happening. What's happening is fairly clear. I think the naming of it is a bit that's kind of confusing. The satellites got created by extra lumps of stuff, and it was just it wasn't close enough basically to get sucked into the planet. So it stayed outside just the catch of the planet, falling around and around and around. By the way, the reason we started this is because you want to know the difference between speed and between scalars and vectors.
Yeah.
Yeah, do you remember that? That was like a while ago now.
Yeah, I was just
But here's the
hoping
reason
we'd
why
just forgotten that bit, because that bit's pretend, whereas this is actual things.
Here's why it's important. If you just say the speed of something in space, it means nothing, right? But if you see the speed and the direction, when you're spinning around something in orbit, you're kind of always avoiding being caught by the planet. Like when we send up a rocket, we send it and we shoot at exact speeds, like 17,500 miles per hour. So it's always falling slightly away from the planet, but never falling towards it. So that's how we keep something in orbit. You keep it falling, but never so slowly that it falls back down to Earth. It's always just slightly ahead of Earth's pull. It's like surfing a wave that you never quite crashes, and you're always kind of doing that. Okay, so its speed doesn't change, but its direction endlessly changes. Its direction changing all the time in a big round, and that's why it's important to be able to say something has both speed and direction, because it's clearly changing, but just its speed is not changing. Has that in any way helped? You have very much put on a sour
And which
face.
one is that? Is that a vector then?
That's a vector, because vectors are bigger and better and more important. They have two.
Does
they contain
north
two
and
pieces
east
of
and
information.
west still happen in space? Do you still have...
No.
How do you do
they're all
directions in
relative. They're
space?
relative.
Why are you
Oh
laughing?
my God, it's incredibly.
Where would the map point?
I don't know. Well, how do you do directions in space?
Well,
Well,
you have to pick a point
north.
and
We
be
only do
relative
north
to
and east.
that.
There are. It's all very. They're very complex since it changes. I mean, for all that's very complex, we can call up an app and you can tell where every star is. It's quite mechanical. It's quite clockwork. Space in a certain sense. That I can tell you exactly what star is exactly in that direction in 1,000 years. So it all spins around. It's amazing how it does it, like whatever. And so on any, you can get an app on your phone and just go, right, well that's, and it will automatically tell you very easily, are you pointing this way at this time? Yeah, that'll be Ursa Major or whatever there. So it's all quite mechanical.
Do you actually navigate by the stars then if you're sending a rocket out?
No, you don't. You don't navigate by the stars. No. Sorry. See what you mean? No, you don't. But when you send a rocket out, you have to constantly recalculate because everything is moving. If you're going to the moon, and what you're actually doing is, I don't think this is going to help in any way. When you go into orbit, you don't just. I mean, for example, space thing goes past the ISS. That's the one that's constantly going around us.
Oh my God, that's my worst nightmare, that thing. Ugh.
Being the size of it, or being up there, or getting
being on it. Can you imagine just like being in a fucking Holiday Inn, but with terror at every door?
With all
just
kinds
horrible,
horrible. It'd be all just people talking about science. Yeah, it would be. It's most people's like bucket list greatest thing they could possibly do in their life. But then, look, that's fair enough. Anyway, that's only 250 miles above us. It's really close. But it's moving.
Scalar, quantity.
Whoa! Yeah, well, that's a scalar. That's
Yep.
it's just a distance. Yeah, that's above 250. Yeah, but it's spinning around, and people are floating around, right? Floating around up there. That like they're in microgravity. It's called. There's no gravity on them. And that's not because there's no gravity up there. It's because they're falling. They're in free fall all the time. If you got a 250-mile ladder, and climbed up to the 250-mile ladder and stepped off, you'd not there. You'd fall right back down really, really quickly. It's only because it's like when a lift goes down and for a second you feel lighter.
Yeah.
Right. If the lift dropped, you would float. You'd hit the ground, obviously. Before you hit the ground and were crumbled, you and the lift would fall at the same speed, so you'd have no weight within the lift.
Yeah.
So you would be weightless as you fell. Okay, that's free fall. If you jump, if a parachute jumps out of a plane in a box, it might look like he's just in a room, but they're both falling at the same time, and so you will be weightless within the box. You'll clearly both be falling. You'll be dragging down, but you'll be weightless within the box. The International Space Station is falling all the time, falling. So that's why they feel like they're weightless. But there's tons of gravity up there. But they're just falling. They're just constantly in a lift that's dropping at full speed down to the ground, but it just misses. It keeps missing. It's on a perfect path to just keep missing the Earth. So it's just falling in a big circle all the time.
Oh, it just sounds horrible.
Really
Would you go?
Yeah, I'd go in a shot. I'd go, but I'm twice the size of most astronauts. They're all 5 foot nothing, and
are they all like jockeys?
They're very much like jockeys. They're drawn from the same gene pool as jockeys. So it's it's either one or the other. If you emerge that size, you're given jockeys. It's either that, jockeys, or cleaning mills in like Dickensian London.
Yeah,
where the 3 options open. It's very small. You could go up chimneys. That's it. That's the only thing you can do. And so in many ways, their potential, their lives have improved enormously since Dickensian times. From cleaning mills to jockeys to astronauts. That's quite a journey that the small have had.
It's huge for us. It's huge. Our community's delighted.
Yeah, I'm very proud of them and what they do. But no, it absolutely would go up. Yeah. It'd be amazing, but you're just falling all the time, falling. Do that sound? That's the sound you have to.
What's your favourite thing in space?
Look, of the many things in space, as you put it, like it's grand.
It can be a type of thing, like a flavour, like I love suns or whatever.
Yeah, no. Do you know what? I love nebulae, which are big clouds of gas. Which are after they go supernova. So some stars, depending on the size of a star, sometimes they explode, go supernova, and they expel all their everything that's in the star, all the stuff they've made, all the heavy things they've made, and they explode them out, right, into a big cloud, right? And that cloud becomes and those clouds become nebulae, which become then the place where more stars are built, because clumping happens and they create stars. So there's big massive clouds of dust in space from which stars are created. They're very beautiful. Some of them are ones are like called planetary nebulae, which are just like a ring of you've heard things like the Crab Nebula and things like that, those things mentioned, or Orion's Nebula. They're these brightly lit sort of clouds in space.
Oh, they look like really screensavers.
That's my favourite one.
Exactly. They are the most standard, bar fish. Reefs. They are your bog standard.
Is that light refracting off them then? Is that why they get so colourful and beautiful?
No, these are all
what
colourised.
happens is they are colorized, and there is energy coming off them, but it's because they are heated. They're slightly heated within a very, very dark universe, so they're emitting energy. Some of them, if you type in Dumbbell Nebula, have you got a thing there that you're looking at? Dumbbell Nebula, what that is literally, the way it's in a circular shape. That is the cloud of stuff expelled from an exploding star. So at the heart of it, there's a core to that, and that is the outer shell of stuff. And it was in a massive explosion millions of years ago, but it's still slightly hot from that, and it's sending out bits of light, in different colours. So you can actually see that. That's what you actually stick a camera at that, and that's what you'll see. So that's the round core. There are other ones which are big clouds as well. So the Orion Nebula, for example, if you look at Orion Nebula, that's just a big cloud of stuff. But it has absorbed and is emitting light, showing, so it picks up light and it sends out energy. That means that we can see it. So those things are cool, and there's loads of them in space.
And those will eventually re-clump, right?
They within those areas, stars will be created. Yeah, I mean, they cover vast amounts of space, and stars will be created within those, because, the clumping will happen again.
So does a solar system always starts with the star, the solar?
The star.
And then everything else
Clumps.
Is kind of the extra bits that's left over after it, yeah, absolutely. And there could be more than one star in a system. Sometimes two stars create that, and they're close to each other, so they end up going around here, like in Star Wars. There's a planet that Luke looks out and sees two stars in Tatooine.
Actually fighting.
They just end up in a kind of a complex dance around each other, and there are planets that circle one or the other. And then on that planet you would see two stars, and you might have no night, or you might have bits where they're both on the other side, but you'll see two stars in your sky. There are triple ones as well. I
just can't imagine understanding this planet well enough to worry about learning about all this as well.
It's one because that's all right to look around it, but if you look up, there's an amazing amount of information that's come to us, and because of what we've learned from up there, we know better how this works down here.
That's a good point. All right. Yep.
Yeah, and actually the thing is, at some point in our history, in a long way, we'll be long gone. You won't see anything because the universe is expanding, and eventually stuff will be too far apart, and we won't be able to see. No light will come to us. And we won't be able to learn anything about life on any other sphere. We'll be gone. We'll be long gone. It'll be really cold.
I hope so. I don't want to survive.
It's thought how it all ends. It all just thins out. And everything just stops. It all runs out of energy. So you don't have to do, for example, the Big Bang. You don't have to do that.
What? No, sorry, say that again. I was really depressed for a second. I didn't listen.
Yeah, I'm sorry, the heat death of the universe is quite depressing. But you don't have to do the Big Bang then at all, do you? Or
no,
the Big
not
Bang
in the combined one.
You're missing some of the better physics, because at least there's some poetry to space. A lot of physics, and I will say this, is actually
it sounds more like chemistry, though. I think so far this has mainly been chemistry.
Well, no, because a lot of it's to do with gravity, and the force that brings all these things together is gravity, and that's not a thing that really features in chemistry. It doesn't really work on a small level. So it's you're talking big scales and how it all works. Like chemistry is a different thing entirely. But it's a pity, because this kind of stuff is the poetry. This is the bit that, there's a lot of stuff that you're doing about springs, I'd imagine, and light passing through one medium and the next medium, and that sort of feels a bit like low stakes, I would say, for physics. Yeah. It feels like there's not a lot of very interesting things happening there, and it does feel kind of like, no, you're not allowed to play with the real yo-yo until you've just learned how to hold the string on your finger, and you have to learn how to do the whole string. It feels like a lot of that, like whatever you can ride a bicycle once you've done the 7 trainer wheel bicycle. When you've learned how to, when you show me that you can do stepping on a pedal, right, or something.
Roll a ball down a hill.
This course is really not the thing, and the reason people get into this is because you read outside the course, is because you read a book at 14 that tells you what the shape of the universe is, and you go, oh my God, and your brain go, and that happens. And then, because this is not going to turn you into wanting to be a physicist at all. Because if I put more weight on the spring, if I put twice as much weight in the spring will go twice as far. How exciting. It doesn't feel like I'm really doing anything amazing here, John. So, but it is unfortunately just a training. It's weirdly like this subject exists to train the tiny percentage of people who will carry on all the way, who you can't pick out now who they are, but when they get to the point where you find out who they are, it's really important that back then you taught them all this stuff.
Right.
You know what I mean? Yeah.
Why did you get into it then? Were you good at maths?
Because I had a teacher who went off piste at a point in the Irish education system where there was a gap where we didn't before we did the syllabus, and he said, "Well, why don't I just teach you?" And he taught us loads of stuff. He did in the sex education classes, which were exciting, in a Christian Brothers school, because the headmaster walked in and he'd drawn a penis on the board accurately, or fallopian tubes or something, and he stood in front of it when the headmaster came in and said, "Oh, hello, yes, we're doing very well," blah blah blah, and we were all like, because we were really on board with the fact that, oh God, somebody's actually going to teach us this stuff. And then the headmaster went out and he stood back going, like, that was the level to which we all felt this is a secret meeting that we're having in which somebody will finally explain to us what sex is. But then, as well as that, I'm not saying those lessons were very important, but as well as that, he then went, oh, look, black holes, and they do this, and there are these massive destructive things where a star collapses in and all space gets bent around it, and if you fall into it you can't come out, and you're like, wow, what's that? And so I read more stuff out. 14 is a magical age for this. The stuff just kind of gets in your head.
So where are you if you're in a black hole?
You're gone. If you're in a black hole, you're a tiny dot.
It's like what? Because all your matter's been squashed.
Squish. I mean, as we said, we're talking about squishing. It's an extreme star. It's a really huge star that did all this stuff, and yet there was loads of it over. And eventually, the burning of the stuff keeps the star from collapsing. Essentially, because when you're squishing all the stuff and all something's made, that pushes the other bits out. But it's eventually, you run out of things to burn, and they just keep coming in. And sometimes you create a thing called a neutron star, which is an incredibly dense star at the end of its life. It just becomes like a thing that, if you hold a spoon of it, would weigh the same as New York City. I think that's the general comparison drawn. It's incredibly dense. But sometimes
it's just loads of neutrons all stuck together.
Yeah, it's just loads of, and so just squeezed in really, really tight. And I don't think it's just neutrons in the thing, but anyway. But it's
neutrons are the mixing desks.
Sound engineers, yeah.
Sound engineers.
Okay, I feel that's not a thing that I know.
Atoms are made up of the neutrons of the sound engineers, and then the electrons are coming to a party, and depending on how loud they can hear the music is whether they're going to stay at the party or go somewhere else.
Okay, and the protons, they're throwing apart.
It was because the electrons are negative, so they're sad in Laura's world.
Yeah, sad boys.
The protons are positive, Bob Marley giving out positive vibes, and that keeps the negative
playing
sad
the music.
Boys. But then the neutrons, they're neutral. They're just sound engineers. They're just
Okay, within the situation, presumably the protons are single people that the electrons want to hook up with. That's important.
The electrons hook up with each other. Electrons only, they're little emo couples. They sit next to each other on the bus.
The electrons don't hook up with each other because they're all the same charge. They repel each other.
Yeah, but sometimes they like to go in pairs.
They pair up in the valency shells.
Yeah.
Yes, but they're really pairing up with the protons. This
is the only thing I've understood in a year. Now it's being undone. This is science's problem. He tells you a thing and then goes, but it's not actually that at all.
What happens in the situation is that you've got two atoms and they share two electrons.
Yeah.
The electrons themselves don't come together, but both of the things around them share those two electrons. They both claim them as their own. It's like there's two parties next door to each other, and the two electrons are
they're smoking in the front garden and listening to the music of both parties.
If you imagine there's two parties and they open onto the one hallway, and these two electrons are both in the hallway, so the people organising the party, because it's really important for the people organising the party that they have as many electrons here as there are protons, so that maybe in some sense they can all get together. So there's because the protons have hosted a party to meet electrons, so that's what they really want to do, and they're really sad, the protons, even though I know that if there's if there are fewer electrons than there are protons. It makes them really unhappy. So they seek out a situation where you can have the same number of electrons. That's how they bond. So they want there to be a balance in pluses and minuses. So the protons want the right number of electrons to come along. But sometimes they both are missing one, but ones on the outside are just standing at the doorway. And they're in the hall, and both parties go, well, the hall's part of our party too. So they can both claim the other one's electron. So those two electrons aren't linked together. They just happen to be standing in an area that the two parties can both claim. It makes them. That's
the electron I'd want to be. Just a bit too cool to be on the dance floor.
And you've not committed. Like you're kind of like, there's your actual friends who you like, and but then there's also these really cool people that you occasionally hang out with, like whatever. But you don't want to dump your actual friends.
No, yeah.
But you also want to keep in with these new guys you met, because it's like first year in college and like whatever. And you might end up eventually dumping your actual friends and hanging out with new shinier friends. But for the time being, like you don't want to be accused by your original friends you came with as being, oh, you're such a user. You brought us here and actually you don't want to be here. Yeah. So that was totally me. Those electrons are keeping their options open.
Yeah.
God,
they're more exhausted than the sea. There's so much going on for everything, isn't there?
There is a lot going on, like whatever. So that's what they're doing. Okay, I now get it. and the neutrons, you're absolutely right, are just running the tuck shop at the disco. They're not influenced by anyone. They're the parents who've come to collect people, or they're the teachers who are. They're the teachers. They're the teachers and the teachers. Oh, so you've chosen a thing. Why am I ruining it? But they do nothing. Anyway, the point is, neutrons are in the neutron star. If it's a really big star, it's so big that even squishing down the neutrons that side isn't enough. It just goes and it falls behind a certain limit, and it falls down to a point, and that's a black hole, and it becomes this area in space. It becomes a point of almost infinite density of this, and everything that gets near it will get sucked into it and get squished into this thing as well. Because the gravitational pull of it is so huge.
What happens? Everything just...
Things fall into it all the time. Things fall into it, stars fall into it. They
No. What? How do you do... And then where is everything?
Stars all the time. And you see it because as the stars are coming, like, say, sideways on it, and if you imagine, let's see how I'm going to do this.
Just crab walking into a black hole?
Yeah, if you imagine... Okay, sorry, why does it occur that you want the waitress is walking past your table, but you go, hey, and you pull the waitress, but she's got a tray of stuff. The tray of stuff often gets fired off as you pull the waitress towards you. This is kind of sounding sleazy, but like the waitress flings the tray out, and we see the tray. And we go, oh, hang on, what's happened here? Why is there a tray being flung? Why is this loads of other stuff being sent up? Because it's being torn off the planet as it falls into the black hole, and this stuff is sheared off, and there's a massive amount of radiation released when it happens. So you can see the effect of it happening in various ways. But they're astonishingly cool, but they're the most destructive thing in the universe. You fall into it, you are gone. You get to the point you get over the event horizon, nothing is happening. Nothing is happening. You're not getting any message out. You're not getting a light out. You can't even...
But are you still alive in there?
Oh, no, you're not. You're really not. No, you're not.
No. I don't know which is worse now. Eventual heat death or black holes.
You've got to say...
would be quicker.
You've got to save the black hole week.
Yeah.
That'd be like... Because you're gone. And you're spaghettified. Because the difference in gravity is so extreme that it pulls you, extends you really sharply, and you just get whoosh.
Hawking radiation, I believe, is a thing with black holes.
Yes.
Hawking radiation?
Yeah.
Like Stephen Hawking?
Yeah,
okay.
I think so.
The
Hawking
second best science interview you've done,
Hawking
except for this one.
was discovered by Hawking, and I once interviewed Stephen Hawking in his office, and he had the formula for it up written in chalk on the board, and you're kind of going, there's no reason for you to write that. There's no reason for that. Like, that's clearly there, so that over our shoulder, the formula for Hawking radiation is there. And what Hawking radiation is basically that the black hole seems to be sitting there doing nothing, but every so often particles appear and disappear in space because of quantum stuff. They just appear for a while, and they usually, particle and an antiparticle appear, and they kind of appear and they disappear together. They kind of appear and then they wipe each other out, and that happens all the time because quantum is
covered
really
antimatter
weird.
yet.
Yeah, and matter and antimatter appear. But if it happens to be near a black hole, one of them goes into the black hole and the other shoots off. And so it all balances out, but it does mean that a black hole is slowly emitting energy. And the energy it emits means that it slowly gets smaller and smaller. So even the black hole, long term, eventually gets smaller. It emits loads of Hawking radiation, which is really difficult to pick up. It's incredibly difficult to sense Hawking radiation. It's really, really faint. But the black hole gets smaller and smaller and smaller and smaller and smaller, and then it goes. So even it suffers from heat death.
God, there's just nothing happy about space, is there?
There's amazing things about space. It's just,
It's
enjoy
just
them,
dust
enjoy
and
them in the
eventual
now.
sad loneliness.
Long term.
I knew I should have had dinner before we did this, because now I just feel really sad for everything. That we're all just
you
like...
can still have dinner. You can still, are you just going to push the food around the plate going, none of this matters?
What's the point? Eventual heat death.
What was it? Broccoli, or flinging broccoli against the wall going, blah, we're all going to die.
Well, I'd fling broccoli whether I was depressed about space or not.
fair
It's
enough,
disgusting, but...
Fuck a pie against a wall. It'd be grand. Yeah. It's grand. But hang on, that was got into where. Oh yeah, black holes. Black holes are great. They are amazing. They're amazing. Yeah. And occasionally a black hole will bump into another black hole, and it will send out a wave of gravity, which can only be measured by setting up an L-shaped, like two tubes, like 90 degrees away from each other. So imagine an L shape, and you've got a laser and a laser on each of those, and they're pinging lasers off each other, and then you'll notice that they'll go out of sync because the whole shape of space will go change because the gravity wave from the explosion is so huge, and then and you'll be able to measure how the shape of space changed. You enjoying that?
What is space? What is space? Because our air is air, but in space, what's space air?
It's a space that the air is within.
What?
I thought you meant on a sort of a more almost like a philosophical level of what is space in relation to each other. But no, you mean what is up there.
No, it's a great question because it's expanding. Yeah. Space is expanding.
No, what?
Yes, space.
But what is it?
No, she's asking are you in some kind of soup when you're up there?
Yeah, is there?
No, you're not. You're not in. It's
nothing.
It's nothing. It's genuinely nothing. But the nothing is expanding.
That can't be because it isn't anything. Yeah. So more nothing's getting in.
No, nothing. No. Just the nothing itself just is expanding.
But if it's nothing, how does it get bigger?
It just does. Space gets bigger. Space expands. There's no reason for it not to get bigger. It expands. And for example, what happens is you won't it's not like everything magnifies. Everything moves further apart. So you'll just move slowly apart. Everything will just move. Things will stay the same size, but space will just move them apart. This gets really kind of weird at this point.
Yeah.
And you don't want to get to the limits of the observable, that whole stuff
But then things have atmospheres because of gravity holding
holds
elements
gases around planets. Yeah,
within.
holds gases around planets. Yeah.
Crikey.
That'll all carry on. That's all fine. That's great. You just enjoy that. We basically swim in a sea of gases. That's what we're doing here.
Yeah.
Yeah, and it's like if I when you throw a paper airplane, it's just basically skimming along an ocean of gas, of molecules, of air molecules. It's bouncing along.
But those aren't in space.
Everything's in space, but they're not out. They're not out there. Yeah, obviously, what we think of space as being that boundary is that bit beyond.
I can't think about us as being in space because then I feel sick. I do not like the idea that planet Earth is in space.
We're clinging on.
I think space is a thing outside of Earth.
That'll be absolutely fine. It will certainly be fine for the combined subject. The space is an area. The space is a place beyond the clouds. You go beyond the clouds, space starts. And
I can't cope with the thought that I'm in space. I don't want to be in space.
We're travelling at 30 kilometres a second right now.
No.
Yeah, you just don't feel it because you're not accelerating. You're just travelling there. It's constant.
Which direction?
Around the sun.
Around the sun.
So we're doing the falling thing. Always just in front of the falling wave.
Essentially, yeah. So you don't feel the force of it, except we're not, except that we're sitting on the thing, so we feel the gravity of Earth. We don't feel the gravity of the sun. So we're certainly falling. Yeah, we are. So so we don't. That's an interesting one. But we don't. It's grand. Yes, because we're in our own localized thing that we feel plenty of gravity. But we don't feel. You're right. We don't feel the weight of the sun.
No.
The windows in the morning go. Up
But the planet does. Otherwise, we wouldn't circle it.
Yeah, so the planet does. We all do, but we just don't. We
just disregard it. We're more moon people. We're moon people.
We are in many ways. We're moon people. But being a moon, imagine then a moon person goes onto a moon. How mad would that be?
Which planet has the longest year then?
Oh, you go all the way out to Uranus. Uranus will be the longest year. Or Pluto, if you want to include for the whole thing. It's like,
I believe it's Neptune at 60,000 days.
Wow.
Yo, sorry, I want to say, of course it is. Yeah, yes, Uranus is the seventh and Neptune's the last, sorry. Starts with the sun, ends with the sun.
Uranus 30,000 days, Saturn 10,000.
Yeah, it's as you go further out.
That makes sense, yeah.
Yeah.
That little rhyme is all screwed up now without Pluto. You know that My Very Energetic Maiden Aunt just swam under North Pier? That's all dead now.
Start with the sun, end with the sun. That's the way I always remember it. Because you can kind of make up the 1 to 5 in the middle. The sun's in the middle, right? Yeah. And then it's sun at the end. Saturn, Uranus, Neptune. And then you can probably work out that Jupiter comes before Saturn, and then you just have to remember obviously Mercury is the one nearest, and then you just remember we're the third rock from the sun.
We've got very different brains though, Dara. You're saying just remember it. I just remember it.
Well, Mercury fastest. We're the third rock from the sun because it was a sitcom, and then you so then you just got to remember Venus and Mars. So the one that I found out different, like I just did there, is remembering as a Neptune and Uranus. Starts with the sun, ends with SUN.
Yeah,
so that's how I always remember it. But
nice. Ron, have you got any more year stuff that we need to cover before we say goodbye to the regular listeners?
I've got some year stuff.
I think we say goodbye to the regular listeners probably an hour ago. Because, I am aware of there being two Daras and people going, oh great, maybe it'll be fun Dara. Oh no, it's not fun Dara, it's the other Dara. It's that other Dara who insists on knowing a bit about this and going on about it as if he genuinely knows a lot. So.
I think that's what our listeners are here for. I'm always very surprised because we call it a comedy science podcast with the emphasis very much on the comedy more than the science. Yeah. And I do try, if I like a subject, we will learn it. But I don't have the functioning concentration for the stupid bits. But I'm always amazed how many of our listeners work in science and use this as light relief to remind themselves why they like their subject.
Oh yeah, we've got doctors listening to this. It's worrying.
Yeah, there's people that listen to it while they're working in the lab, and you just think, does it not just give you a nosebleed listening to us arguing about paella and how it affects a vector?
No, because from talking to that, they're thrilled to be. I think we're all really enthusiastic about it, and we're like to talk shite about it, whatever. I mean, they're probably more like to be bored by me badly explaining things than they are with you funnily not getting them. That's probably, because I'm supposed to know a bit about it. Although what will happen is obviously that somebody's going to come to me after and goes, oh, I heard you on that thing. Did your mate Brian Cox tell you all that? Which, you get a lot of.
I think the big problem will be why are you advocating for minstrel shows will be the big takeaway from this. Look, the super minstrel.
If they rename the suite, that'll be Lee Anderson MP, and various people will be furious if they rename it going. It's been a perfectly good name for that suite for generations. There's no reason for us to get rid of it. Yeah.
But no, we are gonna say goodbye to regular listeners now. So if you are not a patron, this is where we say goodbye to you. Thank you so much for listening. If you'd like to become a patron, go to patreon.com/Lexx Education to support the podcast and to see this final part of the interview and to see the video version of this interview.
And all of the other great content.
Oh, and all the other other lovely stuff we do. You've got Agony Dad. You've got Detentron.
Pop
you've
quiz.
got Pop Quiz.
Class Clown.
Class Clown, where we discuss laughter theory, a thing I actually know and care about. Also, we will be at the London Podcast Festival this year. Please go and get tickets for that. Come and see us live in September. But hey, thanks for listening.
Class dismissed.
How? Every time. For a full year on.